Welcome back to the deep dive. Today, we are tackling a phrase that feels like it's everywhere. Adaptive intelligence.
Oh, yeah. Every billboard, every startup pitch.
Exactly. It sounds impressive, right? I mean, who doesn't want their tools to be adaptive? But when you actually peel back the layers of what we all just call AI or machine learning, well, for most of us, it stops being a concrete thing and it starts looking a lot like a black box.
That's the common perception. It feels like alchemy.
Right. You feed data in, some kind of magic happens, and then an answer just pops out.
But the reality is so much more grounded. It's engineering,
Well,
it's math. And that's why I'm really looking forward to walking through this document today.
what are we looking at?
It's a presentation called From Data to Intelligence, the Architecture of Machine Learning. And the mission here isn't to, hype up the future of robots. It's to literally look at the blueprints. How does this stuff actually work right now?
Okay, I like that. So we want to move from this vague idea of algorithms to a real concrete understanding of how raw, messy data gets transformed into structured adaptive decision making.
And we're going to do it systematically, page by page.
Because the flow of this thing really tells a story.
It does. It moves us away from thinking it's a magic brain to understanding that intelligence is actually, it's a specific set of architectures. It's a toolbox.
Toolbox. Okay, so let's get right into it. Starting with page 1, the document sets the stage with this visual, the architecture of machine learning.
And it's quite striking visually.
It is. On the right side, you've got this blob of unstructured data input, and it just looks like absolute chaos.
Yeah, triangles, circles, jagged shapes, all floating in a void. It's noise.
And that visual is so important because that chaos, that's the real world. That is what data actually looks like before we get our hands on it.
It's not a neat Excel spreadsheet.
No, it's pixelated images, it's garbled audio from a phone call.
Messy text in an email, all of it.
And then in the graphic, there are these arrows pushing all that chaos into the center, into a layer called processing and abstraction. And then out the other side comes this glowing, perfectly organized blue sphere.
Yeah, the structured intelligence output.
And I feel like that word abstraction in the middle is doing a lot of heavy lifting here.
It is. The goal isn't just to organize the shapes like putting all the blue ones in a pile. It's to understand what the shapes represent.
I see.
And that is the core journey we're tracking today. How do we build that bridge from the messy, jagged shapes to the perfect, useful sphere?
From just collecting data to actually making an adaptive decision.
Exactly.
Which, brings us to the fundamental question. How is this any different from the computers we've been using for the last 40, 50 years?
And that's the perfect lead-in. If you flip to page 2, titled Moving Beyond Rigid Rules, it lays out this exact distinction.
Okay. This is the aha moment for anyone who's ever tried to write a line of code.
I think so. On the left, you have traditional computing.
Right.
And it's visualized as this very linear flowchart. Very logical.
Kipquip goes down, hits a decision point, if X is true, and then it goes to then Y.
The classic if this, then that logic.
Right. I tell the computer, if the user clicks the green button, open the window. Simple.
Exactly. But think about what that requires. It requires a human you to write that rule explicitly. You have to anticipate every single possible scenario.
And the slide notes a critical flaw with that. It says it's brittle.
Brittle is a harsh word for tech.
It is.
But it's so accurate. If a scenario pops up that you didn't pre-program, say, the user clicks the button, but their internet is down.
Or the data format changes slightly.
The system doesn't guess.
Yeah.
It fails, it crashes, it throws an error message because it just lacks the instructions to handle the unknown.
Okay, so contrast that with the right side of the slide, machine learning. The visual here isn't a straight line anymore. It looks like a web, like a neural network.
And the keyword changes from explicit instructions to pattern recognition. Instead of you writing the rules, you feed the system data, tons of it, and you let the statistical models figure out the relationships themselves.
So instead of me telling the computer a cat has pony ears, I just show it a million pictures of cats and let it figure out what a cat looks like.
Roughly, yes. And that's what makes it adaptive, which is the key takeaway here. If the data changes, the model adjusts. You don't have to rewrite the code line by line.
You just have to keep training it.
Exactly. It learns what to do rather than being told exactly what to do.
That is a massive shift in philosophy, but machine learning is still a huge umbrella term.
It is.
And the document breaks this down further on page 3, how machines transform data into intelligence.
This is where we get into the actual toolbox. People often think there's just one AI algorithm, like a singular brain in a jar. But really, there are different architectures for different kinds of problems.
And the slide gives us 3 pillars with 3 distinct icons.
We've got a clipboard, a magnifying glass, and a dartboard target.
And those aren't random.
Not at all. The clipboard represents supervised learning. That implies a checklist, right? A known answer key.
Okay.
The magnifying glass is unsupervised learning, searching for something hidden without a map.
And the target.
That's reinforcement learning, aiming, missing, and adjusting based on where you hit.
I love that we're breaking it down like this. It makes it feel so much more manageable. So let's dig into that first one. Turning to page 4, we're looking at supervised learning.
Right. And the document uses a great analogy. A student using flashcards.
This is probably the most common form of ML we see in business today, right?
Absolutely. The core requirement here is something called labeled data.
Labeled data. So that means the answer is it's already attached to the question.
Exactly. The diagram shows an image of an apple. That's the raw input. But attached to it is a digital tag that says label apple. To train the system, you don't just show it the apple.
You show it the apple and the answer key.
Yes. And the mechanism here is a 3-step process. First is training. During training, the model just analyzes thousands, maybe millions of these pairs. It looks at the image of the apple and the label apple. Then comes step 2, mapping.
So the computer tries to figure out the rules. It asks itself, what makes this thing an apple?
It starts to notice the curve, the red color, the stem. It builds this mathematical bridge connecting the visual input to the text output.
And then step 3 is prediction. This is when you take the training wheels off.
Yes, you show it a picture of an apple it has never seen before. Maybe a green one this time, without a label. And because it's learned the mapping rules, it can predict this is an apple.
It works exactly like a student cramming for a test.
It does.
But that all assumes we have the answer key. We don't always know what we're looking for.
That's the problem.
And that seems to be where the next tool comes in.
Let's go to page 5, which covers unsupervised learning. This is where things get really, really interesting. The metaphor shifts from flashcards to sorting a bucket of mixed objects.
The visual here is great. You've got a funnel just dumping all these mixed shapes, triangles, squares, circles into a filter. But unlike the last slide, there are no tags.
No labels. The system has no idea they're triangles or squares.
That's the catch. It's processing unlabeled data. There is no teacher. There's no cheat sheet.
So how does it learn anything useful if it doesn't even know what a triangle is?
That's what I'm wondering.
Uses pattern discovery. The mechanism just scans the raw data looking for inherent similarities. It starts to notice, hey, all these objects have 3 sharp corners, or these objects are all the same pixel density.
So it creates groupings based on the structure of the data itself.
Exactly. It organizes them into piles, even if it doesn't have a name for the pile. It just knows pile A is different from pile B.
I see. And the utility there, as the slide mentions, is finding hidden structures.
Right. Humans are biased. We look for what we already know to look for. Unsupervised learning is so crucial because it can find anomalies or connections we didn't even know existed.
Just because it's looking at the raw math.
Precisely.
Okay, so we have the student with flashcards and the sorter with the bucket. The third one, on page 6, feels completely different. This is reinforcement learning.
This is the training a pet analogy.
Or if you're a gamer mastering a video game level, the header is intelligence through interaction.
It's a loop. And the diagram shows this little robot icon labeled agent and a maze labeled environment. That loop is everything.
And it's critical to understanding things like robotics or self-driving cars, I'd imagine.
For sure. The action step is where the agent makes a decision. Say, it decides to move left in the maze.
And then what happens?
Then it gets feedback. The slide calls it a reward or penalty. If it hits a wall, that's a penalty, a negative score. If it finds a clear path, that's a reward.
So it's basically just playing a game of hot or cold.
In a way, yeah. The third step is adaptation. The model adjusts its strategy over and over to maximize those rewards. It's not being told the rules of the maze.
It's figuring them out by bumping into walls.
It's learning by doing.
It feels like the most organic way of learning. But here's the thing, whether it's flashcards or buckets or mazes, these engines don't run on air.
They run on data.
And page 7 hits us with a huge reality check. Intelligence is a reflection of data.
This is, I would argue, the most important slide for anyone actually trying to build these systems.
Yeah.
You see this gauge, like a speedometer, pointing from low quality to high quality.
Right. It says high model accuracy is only possible with high quality fuel. But what defines quality here? Is it just about having a lot of data?
Volume helps, but the slide really emphasizes the diversity imperative. The data set must be representative
Representative of what?
of the real-world environment where the model will actually be used. If you train a self-driving car only on sunny days in Arizona and then you drop it into a snowstorm in Minnesota,
It's going to fail.
it will fail. Not because the car is dumb, but because the data never represented that scenario.
The slide uses the term GI go, garbage in, garbage out.
It's a classic computing term. If your input data, your fuel is limited or flawed, your output is going to be brittle. You can have the most advanced architecture in the world, but if you feed it narrow data, it's going to give you narrow predictions.
It really hammers home that this is an engineering challenge, not just a coding one.
Absolutely.
Okay, so let's look at what this looks like when it works well. Turning to page 8, we're entering the field of predictive medicine.
This is a perfect example of supervised learning in a really high-stakes environment. The context here is identifying patterns in medical data symptoms, test results, imaging.
Things that are too subtle for human observation alone.
Exactly. And the visual shows a chest x-ray. There's a grid over a specific area and a little call-out box that says, pattern detected, early stage anomaly, probability, 94%.
Wow.
Think about the limitations of a human doctor. They might look at 50 x-rays a day. They get tired. Their eyes might miss a faint shadow that's only a few pixels wide.
But the mechanism here, the supervised learning model, it's been trained on historical records, maybe millions of scans where the outcome is known.
So it's comparing this one patient's x-ray against a library that's bigger than any human could memorize in 10 lifetimes.
Right. And the output isn't a replacement for the doctor, it's an alert.
Exactly. It's just saying, hey, look closer at this sector. There's a 94% match with previous anomalies. It effectively gives the doctor a secondary high-precision set of eyes.
And it doesn't stop at just diagnosis. Page 9 moves on to tailoring treatment to the individual.
And this is where that data representation we just talked about becomes so critical.
This is the shift from standard protocols to personalized protocols.
Right. Historically, medicine has been very statistical. You know, this pill works for 80% of people with this condition, so everyone gets this pill.
But we aren't statistics. The slide shows a silhouette of a person surrounded by DNA strands and medical history icons, and it's pointing to personalized protocol A while graying out the standard options.
Because the model can process your specific complexity, your genetics, your history, your lifestyle. It's predicting that for you, the standard pill might not work, but protocol A will.
But again, the slide loops right back to diverse data in action.
Yes. If the model has never seen a patient with your specific genetic background or medical history in its training data, it can't make that personalized recommendation.
So the fuel we talked about on page 7, it matters so much for accuracy.
It's all connected.
It is. Okay, let's switch gears completely. From the hospital to the bank vault. Page 10 is titled Algorithmic Sentinels, Automating Fraud Detection.
This is a classic cat and mouse game. The challenge, as the slide points out, is that fraud tactics evolve faster than static rulebooks can be updated.
And that goes right back to the brittle rules we talked about at the start. If you write a rule that says flag any transaction over $10,000...
the fraudster just steals $9,999.
Exactly. Static rules are always one step behind.
And the solution presented here is an adaptive defense system. It learns directly from the financial data flow. The visual is a shield with a neural network inside it, protecting a safe.
So it adapts to new tactics without waiting for a human to write a new rule.
Right. It protects accounts instantly, but what's really cool is how it does it.
Okay.
If we look at page 11, a dual approach to security, it shows how different types of learning work together on this.
I like this breakdown. It splits the strategy into 2 layers. Layer 1 is catching known threats using supervised learning.
So this is the flashcard method again. You have transaction data as your input. You match it against a labeled fraud history.
So we know what a stolen credit card behavior looked like last year.
Right. If a transaction looks like that, the output is flag known threat. Easy enough.
But then layer 2 is spotting new anomalies using unsupervised learning.
And this is vital. Because what if the fraudster invents a brand new scam today? There's no labeled history for it. So unsupervised learning just analyzes live spending habits. It looks for groupings.
So if I usually buy a coffee in New York at 8 a.m. and suddenly my card is buying crypto in London at 3 a.m.
That behavior doesn't fit your standard grouping. The model doesn't know what the fraud is. It doesn't have a name for it yet, but it knows it's an anomaly.
And it flags it.
It flags it, and the slide sums it up perfectly at the bottom. Supervised learning catches what we know. Unsupervised learning catches the unknown.
That combination is so powerful. You really need both.
You do.
And it's not just finance and health. Page 12 shows us this is transforming every sector.
Yeah, we get 3 quick examples here just to illustrate the breadth of this. First, retail. It mentions recommendation systems and customer segmentation,
That's the classic people who bought this also bought that feature.
which is really just grouping users by behavior. That's unsupervised learning again. Then you have transportation, powering autonomous vehicles.
Which has to rely heavily on pattern recognition to predict traffic and identify objects in real time.
And finally, finance, trading. It says beyond fraud, ML drives algorithmic trading by analyzing market data patterns.
So it's seeing trends in stock market charts that are too complex or too fast for a human trader to spot.
It's the same architecture, just a different data set.
So why are companies pouring billions into this? Let's flip to page 13, the strategic value of machine learning. This is the business case.
And it really boils down to 3 words: efficiency, insight, and personalization.
Under efficiency, we see these gears turning. It talks about automating complex processes to handle a scale that humans just can't.
Think about scanning millions of credit card transactions a second. No amount of human staff could ever do that. That's scale.
Then insight. The magnifying glass is back.
Revealing patterns hidden in raw data. This is about making better decisions because you can see the reality of your business more clearly.
And finally, personalization. Delivering those tailored experiences.
Whether it's that patient care plan we discussed or a simple shopper recommendation, it's about treating every user as an individual, but at scale.
This brings us to the final concept, and honestly, it's the most inspiring part of the whole document. Let's look at the final slide. Page 14. The future is adaptive.
I love this graph. It plots performance over time. In the beginning, labeled early learning, the line is jagged. It's volatile. It's up and down.
That's that trial and error phase, right? The system is making mistakes, bumping into the walls.
Exactly. But then you look at the curve. It enters a phase of continuous improvement, and the line smooths out and just shoots upward toward adaptive mastery.
The text here says we're transitioning from an era of static data storage to an era of actionable intelligence.
That is the takeaway. The defining characteristic is continuous improvement. In the old world, software was static. In this world, as models get exposed to more data, they don't just get bigger, they get better.
They learn, they adapt, and they refine their decisions right alongside us. It's a completely different relationship with technology.
It is.
It's not a tool that slowly rusts. It's a tool that sharpens itself the more you use it.
Precise.
So to wrap this all up, we started with these messy, chaotic shapes, and we ended with adaptive mastery.
Yeah.
We've seen how we moved from brittle if-then rules to these flexible systems that can learn from flashcards or sort messy buckets or even learn by doing in a maze.
And we saw that whether it's catching a tumor or stopping a bank robber, it all just comes down to identifying patterns in data.
It turns out this big scary thing, artificial intelligence, is really just adaptive prediction based on how good our data is.
That's the reality. It's a mirror. It just reflects the data we show it.
And that leads me to a thought I want to leave everyone with. If the defining characteristic of these systems is that they improve the more they interact with us, if they are constantly learning from our clicks, our purchases, our medical records, then in a way, we aren't just the users.
We're the teachers.
We are the teachers. That's a heavy responsibility.
It is.
We are the teachers in the classroom of the future. Every time we interact with these systems, we're basically grading their homework. So the question is, what are we teaching them? Something to think about. Thanks for diving in with us.
Always a pleasure.
Catch you on the next